This is a brief history of computation. Originally, computers were what is called mainframes. They were very large computers, and organizations would typically only have one. It would take up a full room, and they could run applications and store data on them. But as an application got larger, at some point it would no longer run. There weren't enough resources, whether it was memory or storage or computational power, to run the application. So one of the obvious solutions is buy a bigger computer, but that is kind of financially inefficient, because then what do you do with your old computer that you spent a lot of money on? So one of the things organizations started to do is break their application into pieces that could run by themselves, and they would only put one piece of the application on at a time. So a company might have maybe a payroll system to pay their employees. They might have a bill pay system to pay vendors. They might have an application that tracked their sales. So they would maybe for certain hours, maybe 8 to 10 a.m., put the payroll system on, pay their employees, and then they would back it up, take it off, and then they would install the next application, and it would run for so many hours. The obvious disadvantage to this is that when your application you need is not running, then you don't have access to the data and the application. So it wasn't long before people realized that this approach to computation and building applications just wasn't working. So in the community, people started to try to figure out what are a better way to build applications. And this is kind of a laundry list of what came out of work in the 1970s and into the 1980s. We want to build applications in pieces, and not just like a full application like payroll, but even payroll would have little pieces. Pieces can run on different computers. So if I'm in the payroll system and I want to bring up somebody's payroll and write them a check, that would be a piece of software that stored the application and the data for that, and it would come up and get created somewhere on some computer. When the application is running, we want some smart agent to decide what available computer could run this new piece of the application. This is called load balancing. So what we don't want is the programmer, when the code is written, to decide where the program is going to run and write that into the code. That would not be good, because when you write a piece of software, you don't know out of all the computers you have which one has free resources. That is a decision that needs to be made on the fly when the application is running. So we need some agent. Let's say we have 10 computers running our enterprise software. We need a smart agent to know how much load is on each of the 10 computers: memory, storage, CPU power, etc. And when a request comes in for a new piece of software to run, it can decide which computer to put the software on. We also want and need the pieces to be able to talk to each other using some technology, because you can't just build like these little stovepipe pieces of code. We want to be able to add more computers to the architecture to get more computational resources. So now, if the application gets really big and it's filling up our 10 computers, we could go buy 3 more and then put them in, install, and then we would have an architecture of 13 computers. We need the application to talk or interact or communicate with not just humans, but other computer systems. So if you think about like online commerce, I go to eBay, I buy something, it shows up on my American Express bill. So somehow eBay's computer is talking to American Express's computer. Nice to have is something called no single point of failure. And some systems have this, some do not. So if one computer has an issue, every computer eventually will break, right? I mean, just over time. So if any one computer has an issue, other computers know what it's working on and can jump in and fulfill the request. So if you're a user, and let's say I go to eBay and I add something to my shopping cart, and then I go to the next screen, and unbeknownst to me, the computer that stored my shopping cart, that part of the program, dies. Then another computer knows it died, it's monitoring it, and it knows where the work is, and it picks up the work for the next step in the sales process. I think after you add something, you view your shopping cart and then you pay. So I, as a user, have no idea that the first computer I was on crashed. So this is kind of approach that many technologies take, and that is the concept of tiers. So we don't have one computer, we have multiple computers that do every function of an application. There's different ways you can divide it. This is one way. It's a common way, and that is that there's user interaction interface. So we could have a tier of computers that ran the application part for user interfaces. There is business logic. So one example of business logic is if I go to my online bank, and I have $10 in my account and I try to transfer $20, there's a business rule that says you cannot transfer more than you have, and it would produce an error. That's some kind of logic in the application. So we have a tier of computers that handle business logic, and then we often have a tier of computers that handle the database. Typically, computers for databases need a little bit different characteristics, often very large hard drives, things like that. And these computers can talk to each other. So if a user here at the far right goes to my web page, let's say I go to my online bank, and I go in, my network traffic will go into the online bank's data center. It will figure out what user interface computer is available, has some free resources to handle my web page generation. I go in and I do a transfer, and it will pass that request. So the user interface says, okay, this user wants to do a account transfer. It will call a method in the business tier, and that will handle all of the business logic and interact with the database to get my account information, whatever information I need. And then the request gets back, the response gets sent back up through the user interface layer back to the user. So great thing about this kind of architecture, and the lines kind of show computers talking to each other, and they're supposed to kind of be, kind of all of them to each other, or at least to the tier beside them. So great thing is I can just add a new computer. So if my database computers are starting to get overwhelmed in terms of CPU or memory or whatever, I can just add another computer. So now I have 3 database computers, 2 business logic computers, and 2 user interface computers. Also, if a computer fails, it blows up, it crashes, power supply goes out, all of its work is stored somewhere else. And the computer is monitored, and when it goes down, some smart agent will tell another, in this case, the example, a user interface computer goes down, that it will pick another user interface computer to pick up the work. And it makes it seamless to the user. So this is the kind of architecture used with different technologies, but this is the approach to building architectures for all kinds of systems. All of the large web pages, web apps like Amazon and Facebook, and even ones you don't really think of an application like CNN. You think about like 911 emergency systems, where if the system goes down, somebody's going to die because they're not going to get CPR or something. Multi-user games. Sometimes in multi-user games, you even pick like the data center. eBay, Yahoo, military systems, search engines. You think about like Google. Google, I would assume, has a lot of database servers because there's a lot of information to store, not as much business logic and user interface layers. Streaming services, stock markets use this, banks, and more. So that's probably a lot to take in. One question I often get is if we build these pieces of an application that can talk to each other, is there one way, just one way, that the pieces talk to each other? Unfortunately, the answer is no. There's many ways. And there's no way we could cover them all in one course. You can't even cover them all in one career. Some are older methods that aren't used as much, and there's new ones being invented all the time. Even within the same programming language, so if I were to pick Java, there are multiple technologies to do these different things even within Java. So it's not as easy to try to teach this because there's so many different ways to do it. So in this class, we're going to teach a way to do it, but it's important to note that it's not always to do it. So the general approach you would take will be able to be used with other technologies, but the specific technology used in this course is only good for the application architecture that we're building or ones very similar to it. There's also this concept of frameworks that people have built. Typically, frameworks take a long time to learn, but and it only justifies doing it if you're building a large application. So frameworks are pieces of software that you can kind of embed in your application that have code that does things, common things for you already. So here's just a few. There are hundreds and thousands. You can just Google whatever programming language you want, space frameworks, and you'll get a whole list. And each one does kind of a different collection of things. There are user interface, there are data storage, there are a variety of different functionalities. But if you're going to build a large application, let's say thousands of man years, it would benefit to go through the learning curve of learning and using one or more frameworks.